Okay, so Cat 2, lecture 32, infinite sequences and series, and the comparison test. So the comparison tests are quite useful, and in fact those P series tests are used here extensively. Okay, so what does it say? It says, suppose we have two series, sigma AN and sigma BN, and from now on, usually I suppress this n from 1 to infinity or whatever. I just write sigma AN and sigma BN. And let's assume that they have positive terms. Now, we don't assume that it has non-negative term. Non-negative means it can be zero. But if I have some zeros here, then those zeros either, I mean, even if I don't write them, nothing happens. 0 plus anything is 0. I mean, 0 plus anything is that thing, sorry. What am I saying? Okay, so now the thing is that it says number 1, or I. If sigma Bn is convergent and An is less than or equal to Bn for all n, then sigma An is convergent. The other one is if sigma An is divergent and An is less than or equal to Bn, the same for all n bigger than some n, then sigma Bn is divergent. So let me write this down in a different format. So suppose this happens. An is less than or equal to Bn. All n bigger than or equal to n. Now let's assume that this n is also integer. So I have this sigma, let's write k from n to infinity, ak. Then what happens to this? Just look. If I start at any n, really I will get the same thing. So this inequality, when I add them, and I have positive terms, right? I add them, I have positive terms. This sum also becomes less than this sum, less than or equal to. So if each term here, just common sense, if each term here is less than a term here, then just common sense. When you add them, it is less than this. Okay? Just use common sense. If each term here, they're positive. They are all positive. If each term here is less than a corresponding term here, ak, bk, then this sum is definitely less than this sum. Now, I is saying this. I is saying if this is finite, if this is finite, then this is finite. Now, why does it happen? You see, when it's positive, finite means what? Finite means that it has some limit, right? It means that it has a limit, right? It has a limit. Again, we go back to the monotone convergence theorem. What was the monotone convergence? The monotone convergence is in fact this. If, look at this series n starting here is like a sequence that is adding up. It's like a sequence that is adding up. It's positive, so it is bounded from below, bounded from above. You see, this is the assumption that this is finite. So this is a number. And this sequence, when I start at n plus 1, n plus 2, n plus 3 is a sequence, right? Then this sequence is bounded, and being bounded and increasing at each step, I'm adding something, right? So at each step I'm adding something, and so this sequence here is both bounded and increasing. Therefore, by the monotone convergence theorem, it has a limit. It has a limit means that it is finite, or let's say it is convergent. Okay, so it is convergent. Okay, number 2 is saying that if sigma AK is divergent, then sigma BK is divergent. Now, how do we prove this thing? We just say, suppose not. Suppose sigma BK is convergent. Suppose sigma BK is convergent, then sigma BK is finite. Sigma BK being finite, then it means sigma AK is finite, which means sigma AK is not divergent. So if I assume this is convergent, then I go back to this, to a contradiction to this statement. This assumption cannot be contradicted. So if this is not divergent, which means it is convergent, then this should be convergent by part I. So this also uses part I, which used the monotone convergence theorem. So so that's it. These two can give us a lot of insight into some series that they are not easy, or let's say it's kind of impossible to use the integral test. So let me give you examples. I hope you understood from this picture here that what's happening. It's important to see that if this is finite, this is also finite. If this is infinite, look at it this way. If this is infinite, this is bigger than infinite. Bigger than infinite means what? That's also infinite. So if this is divergent, infinite, this should be divergent. Okay. So examples. Now this comparison test has some say restrictions. I will show you. So let's look at this. 1 sigma 1 over n to the power 5, say plus, say, I don't know, 21. Okay, and n starting at 1 to infinity. It can start at anything, doesn't matter. Okay, so can I use the integral test? Well, you might say, well, why not? Because it has, can I use the integral test? Integral test, IT, let's say IT tells me, find this integral, 1 over x to the power 5 plus 21 dx. And you might say, gee, come on, don't give me something, give me any trouble. This is not easy to find. So why should I try this? But then I look at this and see this, maybe I can compare this with 1 over n to the power p. In fact, I can. So 1 over n5 plus 21 is less than 1 over n5, or n bigger than or equal to 1, right? It's not even equal. It's less than. Why is it? Since they are both positive, we can just cross multiply. If I cross multiply, I will get n5 here, and this one here. And these two are, I can go from here, here, and from here, here. So if I have this, I can have this. If I have this, I can have this. These are equivalent. This is true. n5 is less than n5 plus 2, n21, right? So this is true. Since this is true, it implies the truth of this one, okay? So this happens. Now, so what do I have? I have sigma 1 over n5 plus 21, and this is less than or equal to sigma 1 over n5. Or let's not write anything here. So this is in fact convergent by what I call the P-series theorem. Well, sometimes I write test and sometimes I just write theorem. In fact, that's a theorem, but we can say it is the test itself. So this is, in fact, the proof that this is convergent. So after this, we can say this sigma is convergent by comparison test. So let's call these comparison tests. So comparison tests are CT and limit comparison test LCT. Okay, so I like to use these abbreviations because it's not easy to write limit comparison test. That's too much. So okay, so that is example one. Now I can make some changes here. Make some changes and show you the restriction. If I number two, let's say n 5 minus 21. So if n is say 2, so n should start at 2, so it is bigger than 21 anyway. So it's all positive, right? If n starts at 2, then it's positive. But then can I compare this with something? And please don't make this mistake. This mistake is terrible. I can't forgive you to making a mistake like this. This is not less than this. You can't say that. Now maybe after some, I don't know if this is not. Why it is not? Because if you cross multiply, n5 is not less than equal to say n5 minus 21. Right? If I subtract 21, then it is definitely not less than that. It is bigger than that. So now I have seen students just making this mistake and say, okay, I cannot show that it is less than, so bigger than. Okay, bigger than. Bigger than, and yeah, it is definitely bigger than. For n bigger than 2. Now, so what? I'm comparing with this, and I'm saying that this sum is bigger than this sum. And this is convergent, definitely. What does it say about this? Nothing. It is saying that this is finite. It's like 5, 10, 20, whatever. And it's saying that this number, whatever, is bigger than this. Does it say that this is finite? No. It says that this is bigger than a finite number. It can be infinite. So please, 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 this doesn't say anything. Doesn't imply anything. Okay, so don't make that mistake. Don't say, yeah, I know this looks like 1 over n5. So, well, I just say, okay, it's bigger than 1 over n5. So it is convergent. No. No, 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 please. Okay, now. Well, the other one can be this, so let's say, well, that was 3, what the other ones? So 3, let's say sigma 1 over, but you might say this can be done using x minus 5, say, n minus 5. And let's say n starts at, say, n should be bigger than 5, so n starts at 6. Okay, now what? Comparison test. So 1 over square root of n minus 5 is definitely bigger than 1 over square root of n. Why? Why does this happen? Because these are all positive and this is n bigger than or equal to 6. So positive, positive, I can cross multiply. This is bigger than this. Check. Since these two are equivalent, so this is true. Now, if this is true, then sigma 1 over n to power 1/2 will be less than sigma 1 1 over square root of n minus 5. Let this start at 6 to infinite, 6 to infinite, and this is bigger than 0. Therefore, by the p-test, that is divergent. So this is divergent, implies divergent by comparison test. And why is it divergent? By p-test. The p is 1/2. So by p-test, this is the divergent, so the other one is divergent. Don't try to find limit for that, or don't try to find this sum. Okay, so these are 3 examples. 2 of them is using that comparison test, and the one that is you cannot use the comparison test. In fact, number 2 is convergent, but we need something else. Okay, so that was comparison test. Now, what is the limit comparison test? The limit. I like this one because it is more useful than the other one. Except in some cases you cannot use it, but the limit comparison test, which I call it LCT. So this one, let me use the statement, and the book is in fact quite nice. And again, the same thing. Suppose sigma AN and sigma BN have positive terms. And let limit as n goes to infinity of AN over BN be some C. Now this C is a non-negative number, because this is positive. When I divide them, I cannot get a negative number, but it can be 0. It can be 0, but not negative. So let's assume that this is bigger than 0. So this is crucial that it is bigger than 0, not 0. Now then, both sigma AN and sigma BN are convergent or divergent, or divergent. Okay? They are both either convergent or divergent. Now, if that C is 0, then you need something else. So let's assume that the C is not 0. In fact, what you do is you choose, one of them is given to you, the other one is you choose it. So you choose so that that is not 0. Okay, so this is telling me that given AN, find a BN to compare with. Similar to the comparison test, which you are given AN, then you have to find another infinite series to compare with. This is the same. So you have to find another one to compare. So let me give you an example. In fact, let's go back to the example I gave you. So examples. The one was the one I gave you, sigma, what was that? 1 over A5 minus 21, right? So, not A5, N5. And N starts at 2. Okay, so let's compare. We are using LCT. We have to find another infinite series to compare with. But what is it? Sigma 1 over N5, right? Just ignore this and compare with 1 over N5. Okay, so I need this limit. No matter which one goes on top, no difference. So the limit and goes to infinity. Remember that was A and B and no difference which one goes on top. And I can write this one on top, no difference. So n5 minus 21, 1 over n5, and that is limit as n goes to infinity. This goes on top, n5 over n5 minus 21. And remember, this is like x5, x5, so it is the coefficient of this divided by coefficient of this, so it is 1. And this is bigger than 0. So, by the limit comparison test, it tells me either both are convergent or both are divergent. Now let's look. This is convergent. Therefore, this is convergent. By LCT, since sigma 1 over n5 is convergent. So let's write this next. Since this is convergent by the p-test, come on, by LCT, the other one is convergent. And 5 minus 21 is convergent. Okay? So that is by LCT, and the other one being convergent is by the p-test. Let's just call it the p-test, not the p-series test or the p-series theorem or something. So let's call it just the p-test. Okay, so that was a convergence situation. So let's come up with something more complicated. So let's say sigma 2 and 4 minus 5 and 3 plus 102, say, and the denominator is minus 21 and 5 plus and 3 minus 2 and 2 plus 1025, say something, whatever. And let's say n starts at, I don't know, let's n start at 100. I'm not sure at what n I will get a positive or negative number. Might be negative in the denominator. So, yeah, it might all be negative. So, well, so let's write plus. Okay. So, because then n5 will be so large compared to the other ones, and you will get a positive number. Okay, so if this n is large enough, then you will have positive terms. Now, what should I compare with? This is how you find that sigma, the other one. So sigma what? So pull this out, the first term with the highest exponent on top without the coefficient. Don't use the coefficient. So this is in fact n4. Okay? Then extract this, then the denominator is simply n5. So that is n4, this is n5, and this is sigma 1 over n. Okay? Now, limit comparison test. I should divide this term by this. So limit of that term 2n4, 5n3 plus 102, and 21n5 plus n3 minus 2n2 plus 125 divided by 1 over n goes to infinity. This is multiplied by this, 1 by this, and that is limit as n goes to infinity of, when n is multiplied by that, I will get 2n5 minus 5n4 plus 102n, and denominator 21n5 plus n3 minus 2n2 plus 1025. So what is this limit? Well, you can say this is x and this is x. Remember, for x, if I have 2x5 minus 5x4 blah blah blah, then that limit would be 2/21, which is bigger than 3. So the limit is 2/21, the largest coefficient here divided by the largest coefficient here. Even if I had negative, that would be true. But since I want positive, that's why I'm dividing by this. There are situations that you just take it to be -1/n, which is also divergent. But anyway, so let's look at this first. Now, what is it? This is divergent. So sigma 1/n is divergent by the p-test. So it implies by LCT, limit comparison test, the series blah star, the series star is divergent. So they are either both convergent or both divergent, and since sigma 1/n is divergent, therefore the other one is divergent. Now, there is something from, say, pre-algebra. You might say, what happened? If I have A/B/M/n, right? But from pre-algebra, you know that this is the A/B times the reciprocal of this. So that's AN/BM. If you're happy with this, then that's what it is. When I was in elementary school, the teacher told us it's easier to do this. This one times this one goes in the numerator, AN, and this one times this one goes in the denominator, BM. That's the same thing. So I'm used to doing that, not writing it down and flipping and then multiplying. So I'm used to, that's the same thing. Right? I'm not saying that that's something else, no. But I'm used to that. So anyway, this is, because you need this a lot. That's what I did. This n is multiplied by this and 1 by this. You don't have to write it down like this, then multiply. No, just immediately on the fly you can say that this is multiplied by this. The furthest multiplied by the furthest. So these are the two furthest ones. And then the middle ones multiplied by each other. And the furthest goes in the numerator, these two in the denominator. Okay. So in fact, these are the two important examples. Two things. Now, the two comparison tests, in fact, the first one is not that hard to prove, but the second one really needs some work. I'm talking about high level mathematics, but not at this level. So we just use it. We just use these two tests. Now, I was saying that if I have something like this, sigma 1/n squared minus, then you would say, but if I put the minus outside and look at this, if this is finite, which means if it has a limit, which we know it does, if it is finite, then minus this is also finite. This is a negative number, but minus that is also finite. We will see these things in the next section, which I'm not going to stop today. I don't have time, but when I give you, the next section, in fact, deals with things like this. So let me just stop here and see you next time.